All right, I know this seems like it's part 3 because I actually messed up while making the video for part 1 and I have it in 2 parts, but this is actually just the second notes. So you're going to be able to determine based on the shape of the distribution which measure of central tendencies are more appropriate, and we're going to look over reviews and lines of residuals and line of best fit as well. So we'll be looking at some of the stuff that the EOC like types of questions you will have. We're actually going to look at EOC type questions on this too, and answer multiple choice and multiple select type questions. So don't forget that we just talked about bell-shaped, symmetrical, or a normal curve. In the normal curve, the mean, median, and mode are all of the same value, meaning that they're all right here. We use the mean and the spread of distribution, how far the values vary from the mean, to talk about the data if the data appears symmetrical. So if it's symmetrical, it's pretty easy. But what happens if we are skew? So if we're talking about that skewness that we talked about on the previous note packet, when the tail was longer to the left, it was left skewed. And when it was longer to the right, it was right skewed. And we had these pictures also in those last notes. But what you'll notice here is that the mean is pulled farther away from the top of the data when it is skewed in one direction or the other. So actually our median is a better representation of the data because it is closer to that center point than our mean. So it's important to realize that if we have the normal bell-shaped curve, we stick with our mean. But if you notice that your data is skewed in any way or you have any outliers in any way, you need to be looking at the median. So here's why. So think about the scenario here. The mean is affected more by skewness than the median. We should use the median when the data is skewed. For example, if 4 people are sitting at a table and everyone made $50,000, then the mean and median are both what? Well, if there's 4 people, that's 50,000, 50,000, 50,000, and 50,000. So they're all the same number. So the median is in the middle here. So if I do 50,000 plus 50,000 and divide that by 2, I still get 50,000. So my median, or my middle number, is still 50,000. If I average those together, I divide by 4 because there's 4 of them. So my mean is when I divide by 4. So I divide by 4 there, and I still get 50,000. So you'll notice that if we're all sitting at the table, so if we have 4 of us sitting at the table together, and we're all making $50,000, then our mean and our median are both going to be $50,000. But what if a 5th person sits down who makes $1 million? Somebody that is super rich comes in, and we have to add their information to our data set. What happens there? Well, you'll notice that our median is still 50,000. So that does not change. But our mean is going to change. And instead of dividing by 4 this time, we are going to divide by 5. So if I take that 50,000, 50,000, 1, 2, 3, 50, 1, 2, 3, 50, 1, 2, 3, and I add in the 1 million, and I divide that by 5, I have now 240,000. Our mean has changed drastically. And think about this. If you're sitting down, does $240,000 represent everyone that's sitting there? No. That's not even close to 4 of the people that are sitting there, which is most of the people sitting there. The 50,000 still represents the better data. This data all of a sudden gets shot off to the right. It gets skewed right. So our data gets skewed, which means that our mean is no longer the acceptable thing to look at. So did the average salary of everyone at the table increase? No, it did not. Which answer gives a more accurate view of all of the individuals at the table? Well, 4 of the 5 people there are making $50,000. So the median becomes more applicable when our data is skewed. So let's look at this. So we are going to talk about finding all those values that we talked about in our last note packet when we were talking about our box and whisker plots with that first quartile, our median, and our third quartile, and the greater and upper values. So we are going to talk about this. So we need to list this from least to greatest. So the smallest number of hours I see is 4. Then I see a 5 in there. I see a couple of 6s. I see 1, 2, 3, 4, 5 6s. Then I do my 7s. I have 1, 2, 3, 4, 5, 6, 7. So I have 7 7s, I have an 8, and I have a 9. So I need to always start by listing my data from least to greatest. So if I'm finding my mean, I add them all up and I divide by how many there are. So I have 1, 2, 3, 4, 5, 6, 7, 8. So it looks like I have 16. 1, 2, 3, 4, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I do. So whatever I have there, I'm going to divide by 16. So I'm going to add all those numbers up. So I have 4 plus 5 plus 6 plus 6 plus 6 plus 6 plus 6. I think 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Good. 1, 2, 3, 4, 5, 6, 7. I have an 8 and I have a 9. Okay, so that's 105. So I take my 105 and I divide by 16. So my mean is about 6.6 hours. So I have a mean of 6.6 hours. Remember, my median is like that center divide in the highway. I look for the center of it, so I have to go back and forth until I find my center, which this is an even number of data, so we will have 2 in the center. So I add those together, and I divide by 2, and I get 7. So my median is 7. My mode is my most often. My mode is my most often there. And my most often is my 7s. I have 7 7s. And my range is from 9 to 4, which is 5 hours. So we have our mean, median, mode, and range. So the median is here. So we still need quartile 1 and quartile 2. Well, quartile 1 and quartile 2 deal with the median of the center of the data, or of the lower parts of the data. So I'm going to be looking for quartile 1 here and quartile 3 here. Those are, not 2, sorry, 3. Those are, we're going to find the medians again, but only of those pieces. So I'm going to go back and forth. And I have 1, 2, 3. So I have 6 and 6 here, which 6 plus 6 is 12. Divide that by 2 is still 6. So my quartile 1 is 6 hours. And then I do the same thing here, and I find the middle of my data, and I'm between 7 and 7. So I actually have my median and my quartile 1, or median and my quartile 3 are the same. So how did I do each of these things? For the mean, I added them all together and divided by how many they were. For the median, I looked at the whole entire data set, make sure it's listed from least to greatest, and I found the middle, which was between 7 and 7. 7 plus 7 is 14. Divided by 2 is still 7. Mode is the most often. I have 7 7s, which is the most numbers that occur. My range is the biggest minus the smallest, so 9 minus 4 is 5. My lower quartiles, I take my median to my end, and I look for the middle of my lower half of the data, which is 6 and 6 is 12 divided by 2. And I look at, for my quartile 3, I look at my upper half of the data, look for the center again, 7 and 7 divided by 2 is 7. All right, so you're going to have questions like the one here on your EOC. So it is going to be super duper important that you're understanding what it is asking. I know it's kind of blurry for you, but you guys have it in front of you. So the police department captures 30 speeds on a radar and organizes the data below. What can be inferred from the data? Select all that apply, which means that there's going to be more than one answer. So let's remember, this is the median. Because of this distribution here, we are skewed to the left, which means that our mean is going to be pulled this way. I'm not going to say it's right there, but our mean will be somewhere over here because our mean gets pulled when it's skewed in that direction. So it's important that you guys realize that this is skewed left, which means that we have a mean that's to the left of our median. So in this case, is our mean equal to our median? The answer is no, because it is skewed. So that is not true because the data is skewed. Now, if it had been a perfect box, like a perfect bell shape, then sure, it could have been that way. The mean is probably less than 30 miles per hour. Well, our median is 30 miles per hour. Since it's skewed to the left, our mean needs to be pulled to the left, which is less than 30. So that one makes sense. The mean is probably more than 30 miles per hour. Well, no, because it is skewed left, so the mean is pulled to the left. If an officer captures an additional speed of 70 miles per hour, the mean must change. So 70 is over here. If we get an additional speed of 70 miles per hour, the mean must change. So we're looking at this must change here. So it's important that you guys see these words in here because it's saying it has to change. Well, if we're adding another number to this data set, shouldn't the data change when you go to divide that? You're adding them all up and dividing, and it's a bigger number that's in the data. So yes, because the number is bigger than what's in the data. And finally, it says if the officer captures an additional speed of 70 miles per hour, the median must change. This is talking about must change. It is important that we remember that we can have a lot of the same number over and over again. So the median may not change just because we added another number here. So for example, if I added 50 over here, does my median, where am I at, 3, need to change? And the answer is no. You'll look here that I added a 50 on this problem, which isn't there, but it doesn't change my data. So it's so important that you realize that the median, because numbers can repeat, do not have to change. So this is saying it must change. Well, no, it does not have to change. Now the mean will change. All right, next one here. The table shows the distances that schools will travel to attend a field trip to the state capital. School 7 has to travel 15 miles. If this outlier is added to the data, which is true about how it changes the data in the table? Select all that apply. Let's look at this data first of all. This does not have a very large range right now. If you take the 425 minus the 150, the range is only 275. But if we do 425 minus 15, the range is now 410. So this is really going to pull the data. Now think about this. This is a low point over here. So we really need to think about this. So is our data less spread? No, it's way more spread. We just looked at that. So this doesn't make sense. It was 275. Now it's 410. So it's definitely more spread. So do both the median and the mean change? Well, let's look at that. Let's order our distances from least to greatest. So let's start without the 15 in it. So it's 150, 200, 380, 380, 400, and 425. So our median is 380. Our mean here, we're going to divide by 6. So mean is 150 plus 200 plus 380 plus 380 plus 400 plus 425. So that's 1935, and we can divide that by 6. Our mean is 322.5. So this is the original data. That is just the original data there. So what if we put this 15 here now? Well, if I look for my median is still 380. But if I go back and I add this 15 to my other data, I now divide by 7, and I get 278.6. Did my median change? Did my mean change? Well, no, my median did not change. So both the median and median don't change. You can see the work down here. You can do that work. They give you numbers. There is no change in the median and the median. Well, that's false. There's a change in the mean. There is no change in the spread of data. We just talked about how the spread went from 275 to 410. There's a huge change in the spread of data. The median stays the same, but the mean changes. The median stays the same, but the mean changes. Well, that's true. And the median changes, but the mean stays the same. And that's not true. So notice this says select all that apply. That means you could have selected every single one of those options. But the fact is that you can find the mean and median on this problem, and you need to do it with and without the 15. So make sure you guys are doing that when you're doing these problems. These problems might take you a long time, but your EOC is not a timed test, so you get to take as long as you need. All right. Looking at some residual type stuff and our line of best fit we did in October, so this was a long time ago. A residual is defined as the difference between the actual value of the dependent variable and the value predicted by the model. Which graph best represents a relationship that minimizes the residual? So you're basically saying which one actually matches the shape of the data and gets those points as close to the line as possible. Well, first of all, my data is not just going to the left, so that doesn't make sense. And my data is not making an exponential curve, so that doesn't make sense. My data is positive, not negative, so that one doesn't make sense. So my answer here must be D. Now, you'll notice it's actually following the shape that it's going, and it's trying to get those points as close as possible to my line. I'm trying to think if there's anything you guys need to know there. So just make sure you guys are being careful with those. There's a lot of words in here, but really all it's asking is what is the best line of best fit. So if you don't understand what a question is saying on the EOC, just look at this. These don't make sense anyways, so you kind of have to choose D here. All right, a car sales business is analyzing the number of cars sold and the average daily high temperature. The data is shown on the graph below. Which statement is correct based on the data? So this is just saying which statement. It doesn't have an S, so it's not saying it has more than one. So you got to be really careful not to select more than one when you don't have to. So, and it's saying which statement is correct. Well, the temperature gives no indication of car sales. Well, there's definitely something that's going on. There's definitely some correlation here. So that doesn't make sense at all because there is something that's going on with higher temps and higher car sales there. If the temperature is 50, the amount of car sales will definitely be 4 cars. So if you're following this up and over, first of all, it doesn't even follow our trend line. Second of all, it is a trend line, or a prediction line. Prediction is the key word here. This does not mean that's actually going to happen. That is a prediction of what could happen. It doesn't mean that because this point is here almost at 4 that that's actually what's going to happen. Your trend line does not actually mean that that could happen. It's just saying this is a very strong possibility. The higher temperature is correlated to a higher car sale and causes the car sales to increase. Well, we talked about correlation versus causation in October. And we talked about how things might be correlated, but they're not caused. The big thing you guys need to remember is that you can never really imply causation completely. For example, we talked about higher temps, higher crime and higher ice cream sales. These two were correlated when we looked at it in October, but they weren't caused by each other because it probably had something to do with the temperature. So you can never actually imply causation completely, even if it's correlated. So if you ever see this thing that says causes it, you know that can't be the answer. You cannot imply causation like that. So just be careful. So a higher temperature is correlated to higher car sales. That's true. There is a correlation. It's very strongly correlated. That's a very small residual there. But not necessarily. It could be caused by the cause of increase. This is how you want to see it if it's talking about causation. It's not necessarily there, but it could be. So whenever you see anything with correlation and causation, make sure you're looking for that. All right, last one here. Which of the following statements describe the linear model shown below? Select all that apply. Oh, there you got another select all. There could be a bunch here. So this is the number of days of schools missed over math grade. So the number of days missed has no correlation to the student's final exam grade. Well, there's definitely a correlation. There doesn't have to be a causation, but there is a correlation. Those residuals are really small. So which of the following describes the linear model shown? So that does not describe it. So I had to reread that to make sure it doesn't say not or anything weird in there. A student with perfect attendance is expected to score approximately a 98%. Well, perfect attendance is expected is not meaning that it's going to happen. It just means that it's probably a good chance. It's predicted. That is what your line is. It's a prediction line. So since it's a prediction and it's expected, that's a prediction, you can say that. A student with perfect attendance is score approximately 38% on the final. Well, no, our line is not there. We just said it was up here at 98. For each day a student is absent, the student's final exam score is expected to decrease approximately 6 percentage points. Think of this like slope. So number of days and percentage are our x and y. And we do y over x. So it's saying it's going down -6 per day is what that's saying. Think of it like slope. Well, it's hard to see this here, but I try to look at the slope here. It looks like if I choose a point, that's a good even point here. So this one looks like it's like exactly at 70,5. If I go down and over to the 6th day, it hasn't gone all the way down 10. It looks like it could have gone down about 6%. So that one does make sense to me based on what I just did. So I kind of just look at this line and I try to look for the slope, and it looks like it's about going down 6 over 1. So that makes sense. So for every 6th day a student misses, so for every 6th day a student is absent, the student's final exam score is expected to decrease by approximately 1 percentage point. So this is a slope of 1 over 6. 6th day is your x. 1 percent point is your y. So that's -1 over 6. So if you go down 1 and over 6. So I go down 1 over 6. I'm like all the way over here. That is not what is happening. So when you read these, try to read them like slope. Try to figure out which one's your x, which one's your y, and make sure you know that slope is a change in y over change in x. Finally, the following scatter plots show relationship between two variables. Draw a line that correct correlation coefficient. You guys have always done pretty good with these. Remember, the closer it is to 0, the less correlated. The closer it is to +1 is a positive, strong positive. Closer to -1 is a strong negative. So I have two negatives here, and these two are negative, so these two are going to be related, and these two. So between the two positives, which one is stronger? Well, 0.8 is stronger, and this one is stronger. So it goes here, which means that one has to go here. Negative 0.14 or negative 0.176 is stronger. Well, negative 0.176 is stronger, and this one is a stronger correlation than this negative one. All right, you are done with both your videos. Get your homework done. See you tomorrow.